Then we can start.
Thank you. Hello, everyone. It's very nice to be here finally, to be able to join this workshop. Today, I will give you a bit of a pain in the neck, a bit of mathematics, and then I will dive into the challenges that we've encountered with doing the mathematics in a parallel way. So it's straightforward when it's single core and sequential. However, when you start thinking about algorithms in a parallel manner, and the things get fairly complicated. Next slide, please. Okay, so I won't go into the equations that you have already seen hundreds and hundreds, perhaps thousands of times. However, I will focus on the treatment of these equations that we use in our solver. So the momentum and the continuity equation in the implicitly coupled pressure velocity solver are treated in a single system, a single linear system, after the linearization of the momentum equation. Please, Flavio, skip to the next slide. So simple algorithm, 1970s, decoupling the pressure and the velocity. We need to under-relax the pressure field in order to make the convergence of the algorithm stable. However, the coupling, the nature of the coupling between pressure and velocity is linear. And the idea of the implicit coupling, so putting everything in a single linear system, is to preserve this coupling in a single linear system. Next slide, please. And we get an animal, like Herb likes to call it, which looks quite daunting. So we have a very large block matrix where the discretization of the momentum equation is represented in the first row of the matrix, and the discretization of the continuity equation, now transformed into the pressure equation, very similar to the simple algorithm, is put into the second row of this matrix. However, these terms on the elements of the matrix are matrices themselves, and this means that your system will be much larger, creating a memory overhead compared to the simple algorithm. Also, something that is quite challenging is the nature of the equations that are put into a single linear system. So we have the momentum equation, which is parabolic, and then you have the pressure equation, which is elliptic in nature. And the pressure equation represents the largest part or the most time-consuming part of the solution algorithm. So next slide, please. The structure of the matrix, we have chosen to keep the structure of the matrix the same in the block-coupled pressure velocity algorithm. So we have the upper and the lower triangle. The storage is basically the same. The diagonal term, however, these little dots, which represent the elements of the matrix, so corresponding to a very simple mesh on the left-hand side of the image, are non-zero. The same for both simple and implicitly coupled algorithm, but in simple algorithm, you will have in 3D simulations, three-dimensional simulations, you will have 4 of these matrices where these dots will be numbers, so matrix elements represented by scalar values. And with the implicitly coupled algorithm, these little dots will be matrices themselves. Next slide, please. So the unknown vector in the implicitly coupled solver will consist of 3 unknowns representing the components of velocity and 1 unknown representing the pressure for each cell in the computational mesh. And corresponding matrix elements will be on the right-hand side shown here, Aij, will be matrices themselves, where elements of these block elements represent the coupling between different variables in the same cell. So how ux in cell I represent or communicates depends on u in cell j, and so on. Next slide, please. So the structure of the block element in the matrix actually follows the discretization procedure that we use in the normal simple algorithm, meaning that when you write the equations in a block matrix, the little elements of the block matrix, the elements representing the coupling between the variables between different cells, will have the same structure. So here on the top left, you will have the discretization of the momentum equation, where you only take into account the velocity terms, so dependence of different components of velocity. On the right-hand side, top right-hand side, you have the pressure gradient stemming from the momentum equation, so how the velocities depend on pressure. And on the bottom, on the left-hand side, you will have the pressure equation, so the discretized velocity divergence and the discretized pressure Poisson equation. So this is the diffusion equation that we get the same as in simple algorithm. Next slide, please. So the advantages of implicit coupling is that we preserve linear coupling between pressure and velocity, meaning that we do not have to use under relaxation the pressure field. However, the disadvantage is that the coefficient matrix obtained from the discretization will not be diagonally dominant, which is ensured in the simple algorithm. The storage capacity is also 16 times larger, since there may be some zero elements in the block coefficients representing the coupling between the variables. However, we will store all of them. So in this case, even zeros are stored for block elements. And the biggest disadvantage regarding the linear solution algorithms is that we have different types of equations solved in the same linear system, meaning that choosing an optimal, read optimal as efficient and convergent algorithm is quite challenging. Please, next slide. Skip this one because you don't have the animation. So let's go to the next. Thanks. And now I will slow down a bit because this was only the introduction, representing the challenges that we were facing at the beginning of the project. So the choice of an optimal linear algorithm for the pressure velocity system is not straightforward. It's not trivial. And literature suggested that for elliptic equations, the most efficient way is to use multigrid as a preconditioner for Krylov subspace methods. Multigrid relies on resolving the error term. So here you have an illustration on the image here. The first picture, the left-hand side picture, shows the error term for a two-dimensional domain plotted for each computational point or cell. And you can see that at the beginning of the iterative procedure, the error is quite oscillatory, so it is not a smooth function. And when using simple iterative procedures, the so-called fixed point methods, such as Gauss-Seidel or Jacobi, it relies on smoothing out the error. That is, these algorithms, due to their locality of exchanging information about the error term, will smooth out the error. So the error will now look like a nice function, which can be efficiently interpolated. And this is the idea of multigrid. So if I have a nice smooth function, I can go on to a coarser problem, meaning in geometric multigrid, a coarser mesh. And for us, algebraic multigrid, meaning a smaller dimensional matrix, a smaller linear system, I will now make the error look oscillatory again. So it will now become, it will not be a smooth function as it was after applying Gauss-Seidel on the fine problem. And if I use the same algorithm again, it will also have the effect of smoothing. And please, next slide, Flavio. Thanks. So in algebraic multigrid, the idea is to create several coarse level linear systems where your basic iterative procedures will become efficient again. The questions that need to be answered and answered very efficiently is how this communication between fine problems, so high dimensional problems and low dimensional problems, how this communication will be done. And here we have two matrices, restriction matrix and prolongation matrix, which are basically projection operators used to project a problem from a higher dimensional, from a higher dimension to a lower dimension, or vice versa. Next slide, please. And what we will do in multigrid is we will start from the fine level problem where we will calculate an approximation of the solution. We will obtain the residual for this approximation. And if you know a bit about convergence theory, you will know that the residual is actually the error term. So how far I am from the correct value of the linear system, the solution of the linear system, projected into another space by the coefficient matrix A. So residual is basically the error scaled by A. And I will use this residual on the course level, where I will solve for the residual equation, meaning that now I'm not calculating the solution of my system AXB, but I'm calculating for the correction of this solution. Why am I doing that? Because I know that this error term, due to the smoothing properties of, for example, Gauss-Seidel, is now a smooth function, which I can efficiently interpolate. And then I will go with this calculated correction term back onto the fine levels, where I will correct the solution of my fine level system. However, this is only a two-level cycle, multigrid cycle. In practice, we will have multiple levels, so perhaps 7, 8, 10 levels, where the only thing that I will control as a user is the number of equations being calculated at the course level. So for example, I will say, create a hierarchy of multigrid levels until you reach a linear system of a dimension 20 by 20. And this will be, this is when the algorithm will stop creating multigrid levels. Next slide, please. So we have chosen to implement the most demanding in terms of iterative, in terms of the number of operations and the mathematics behind it. The most demanding algorithm is the selection algorithm, or the classical AMG. And in this classical AMG, the coarsening, so the creation of coarse level problems, is based on the selection of equations. So these equations will be selected by their influence onto the solution of the entire linear system. To just put it in a simple illustration, on the left-hand side we have a 9 by 9 coefficient matrix, which in course level will become, let's say, a 5 by 5 matrix. And what you can notice is that it became denser. So from going from a sparse matrix in the fine level, where you only have a few non-zero coefficients in each row, you are now going into denser matrices on coarser levels, meaning that you increase your computational cost. And also you have significant memory requirements, since you need to store all the coefficient matrices on each level. Next slide, please. Flavio, please, next slide. Nothing changed. Oh, thanks. So the choice of these equations, which we kept on the course level, is done by identifying equations which are the most influential in your linear system. What does that mean? I like to give an illustration in terms of the computational mesh. So if there is a cell in the mesh on which a large number of its neighbors is dependent, so their solution depends on the solution. For example, here we have equation or cell number 4. This equation, I have an interest in getting a correct value of the solution in this equation. And I will try to keep this equation as I go on to coarser levels in order to use its correction term onto its neighbors. And it's quite, I think it follows quite a nice logic, since if your neighbors strongly depend on a solution which you certainly know, so you have eliminated this error term, you have put the error onto 0, it makes sense to use that solution to correct these strongly dependent neighbors. Next slide, please, Flavio. And if I go into my matrix, this is where I will define the influences and dependencies in terms of my LDU addressing. So this is also a challenge. We are not storing the elements by row and column. We are using, so compressed row, we're using something of a hybrid. So I have 3 arrays and face addressing, meaning that finding these influences and dependencies, which will be used as a criteria to define or choose the coarse level cells, coarse level equations, is quite a bit of loops in my code. So the code is quite long for this reason, for looping through the lower and upper triangle and trying to read the matrix row by row rather than by upper and lower triangle. Okay, next slide, please. The idea of choosing these strong equations, so the strongest equations in your matrix, is, as I've said, to efficiently interpolate the correction term once you go back to the fine level. And this interpolation formula is based on an assumption that the error term between 2 neighboring equations, 2 dependent equations, is in fact linear. So we are using linear interpolation, and this is how the prolongation matrix is formed. So we are calculating the interpolation formula between neighboring cells. The restriction is quite easy. It's equal to the transpose of the prolongation. And by Galerkin projection principle, coarse level matrix is calculated as a product of matrices, which makes this algorithm, again, quite demanding computationally, since you are doing a triple matrix product explicitly in the algorithm. Next slide, please. We can skip this, please. Okay, thanks. So I will give a brief example of an issue that we've encountered when thinking about making this algorithm parallel. Since this choosing of strong equations, so here denoted in blue, so these are the equations that will be chosen as the strongest in your linear problem, the most influential, and their correction terms, which will be calculated, will be interpolated onto the equations which were eliminated. These are the so-called fine equations. This process of choosing equations is highly sequential. So you cannot make it, you cannot do it in parallel and still hope that you will obtain the same convergence as you did in a sequential algorithm. Why is that? Because in the nature or the basic postulate of coarsening is that each coarse equation, so here denoted in blue, will provide its correction to its fine neighbors, the equations which were eliminated. And if you go onto the right-hand side image, so you do a coarsening procedure as we do it in our algorithm separately on each core, you will get perhaps on the processor boundaries equations which do not have an interpolation from the other side. So you have two equations which are both which were both eliminated, and you will compromise convergence here because your equation will be getting their correction only from a single influential neighbor. So this is something that we have chosen to do. So we knew that we will compromise convergence like with this. However, it was to keep the algorithm as efficient as possible, because communication across processors for creating the same coarsening pattern as with a single unit would be quite expensive. Next slide, please. Just a brief comment. So SAMG is the classical multigrid method, and the AAMG, agglomerative or cluster AMG, as they call it, is a bit different. It is a special case of SAMG, where the prolongation and restriction matrix only have ones on their as their elements. So we are doing basically a summation of rows and columns of our fine level matrix to obtain the coarse level matrix, and your prolongation, your interpolation, is injection. So on the left hand side, you see the effect of this clustering algorithm, basically from fine level equation or fine level mesh here shown. You have anisotropic cells, and this clustering, the algorithm for clustering, will persist in creating a more uniform mesh. So the effect of adding equations in your matrix is very similar to clustering the cells in the mesh to obtain a more uniform cell. So to eliminate anisotropy. In this way, you're basically providing spreading of information in your Jacobi or Gauss-Seidel to be efficient in all directions in the mesh. So as you can see on the fine level, the spreading of information is much more efficient in the direction of y-axis due to the face area, which is much larger. Okay, next slide, please. For block matrices, so I have been talking about scalar matrices up until now for AMG. The idea is just to create a scalar matrix which will represent in a certain way our block matrix, and we will do coarsening on this scalar matrix. And this is done by taking the norm of block elements, norm meaning that we only take the pressure equation, so the diffusion or the Poisson equation of pressure, and we base our coarsening on that. There are other possibilities, so taking the Euclidean norm or something like that, but you will see that this didn't provide good convergence. Okay, next slide, please. Also, smoothers for the block system, even though Gauss-Seidel, Jacobi, so point fixed methods are classical smoothers used with AMG, we had to be a bit creative with the coupled system, since Gauss-Seidel and Jacobi did not converge due to the diagonal dominance problems. So ILU factorization was implemented as a type of smoother, which is based on the Gaussian elimination, however, a bit restricted. And also we have chosen to use the Kraut's algorithm, since it is the most natural one with the LDU addressing. In the Kraut's algorithm, we are accessing the matrix elements from the upper and the lower triangle, which is very, very natural with LDU addressing. Okay, next slide, please. Okay, now let's look at the performance a bit. So all of these cases are for the implicitly coupled solver with comparison of different linear solvers. For this case, this is a case of flow through an engine jacket. So it is a block structured mesh. However, there is a bit of anisotropy in the mesh. Next slide, please. And these are the linear solvers that we have been testing. So SAMG, this is selection AMG. Different settings are listed here. The choice of these settings is not trivial. So this is why we have been doing comparisons to see whether any of these settings have an effect on convergence. Also, there are issues like permuting the rows of the course level matrices. So multiplying it with the permutation matrix to change the order of equations on course levels. There is a question of scaling the rows to have diagonal elements which are of the same order of magnitude and so on. And also we have compared to standalone Krylov subspace solvers, GMRes and BICG stub, both used for asymmetric matrices. Okay, next slide, please. And here is a dramatic convergence. So focus on the left-hand side of this image. So this is the convergence of the linear solver in a single nonlinear iteration of the PU-coupled solver. And you can see that the selective AMG converges almost 1 order of magnitude per iteration, which is actually the theoretical convergence of multigrid. So we have been able to achieve a theoretical convergence of SAMG with the coupled system, while other types of solvers which are used or which were used before, so BICG stub, GMRes cluster, or agglomerative AMG, stall at some point and do not even reach the levels of convergence we have reached in only a few iterations with SAMG. Next slide, please. I will skip this due to time limitations, so please next slide. And also this one you can skip as well. Okay, I will just give a bit of a comment on this coarsening procedure. So we have done in the last couple of months also testing on something that is called aggressive coarsening. The idea of aggressive coarsening is to select the equations in your fine system by reducing their number by a factor of, let's say, 5. So if I start from 1000 by 1000 system, I wish to obtain a 200 by 200 system in just a single coarsening procedure. With standard coarsening, we have a factor of 2. So the number of cells is reduced by a factor of 2. In the agglomerative, so cluster multigrid method, shown here on the backward facing step example, the image on the top, you will also get a reduction of equations by a factor of 2. So joining the cells will usually reduce the number of equations by 2. And you can see how the clusters are formed. The colors also denote the order in which the clusters were formed. And on the bottom images, we have different settings of SAMG, which cause different coarsening patterns. So these are the coarsening patterns obtained by SAMG. And you can imagine if we have a diffusion equation, so diffusion in its nature elliptic, should produce something which is, I would say, the most similar to the image on the bottom. So a very nice distribution, very equal distribution of selected equations throughout the computational domain. And this is achieved by a certain combination of settings, which also provides the best convergence for SAMG. Okay, next slide. We can skip this one. Okay, this one also you can skip. This was only a comment that by SAMG, you are obtaining, as you go to coarser levels and you compare to geometric multigrid, you obtain polyhedral cells if you start from tetrahedral or hexahedral, but it's not as important, so we can skip to the next one. And look at the parallel performance of SAMG. So how does the algorithm scale and perform? This was done on a case with 15 million cells, so it's quite a small case since we were running it on our faculty computer, so our group's cluster, where we had a limit of 112 cores. And on the right-hand side, you can see the speed up compared to 4 cores. It's slower than the theoretical linear speed up, since there is a significant drop of performance, so an increased computational effort as we go into a larger number of cores, and we compromise the coarsening procedures, so the optimal prolongation, interpolation, formulation. Next slide, please. We can skip this one. This is the table corresponding to the graph. Okay, and the thing that I'm concerned about, or I'm dealing with now, we have a few cases which in highly parallel computation will diverge. So SMG will diverge, and we have been doing tests to see whether choosing a domain decomposition algorithm or method affects this performance. And this is a very violent, however, illustrative example of using a backward-facing step case and dividing it onto 4 processing units. So one decomposition is very natural. So on the left-hand side, a vertical decomposition where you keep processor boundaries as small as possible. And on the right-hand side, we have a violent horizontal decomposition where you have a large interface between cores. And the coarsening also is shown. So the colors, again, represent the order in which the equations were chosen to be coarse. And this is throughout a number of levels. So we start with the finest level, then we go on to other coarse levels. So the question was whether this violent horizontal coarsening, choosing the boundaries in a very unnatural way, will affect the convergence of SMG. So not the parallel performance in terms of computational time, since I'm doing something which is not efficient, dividing the processor boundary to be very large, but whether this will affect how the algorithm works. Because in very large cases on thousands and thousands of cores, you cannot control how the processor boundaries are positioned and whether you are losing some valuable information for the selection AMG algorithm. Okay, next slide, please. And here you can see the convergence of the linear solver, so SMG, in a single non-linear iteration. This was the 100th iteration. And the black line corresponds to the convergence in the case of the horizontal, the unnatural decomposition, while the red line represents the convergence in the vertical natural decomposition. And you can see that the performance of the red line is what we expect, so almost theoretical or better than theoretical. 6 orders of magnitude drop of residual in 6 iterations, while with the horizontal decomposition, the residual stalls. So there is a problem with convergence, and it is even more evident in the elliptic pressure equation. So this is not due to the inefficient communication between the processor units, the processing units. It is due to the fact that we have split the domain in the direction in which the communication is very important for multigrid. So in the direction of the largest area of the faces of the cells, meaning that I have eliminated off-diagonal elements which are very large in magnitude and which have an effect on formulating the interpolation or the interpolation of the error from coarse to fine level. So this is very difficult to control in terms of highly parallel simulations. And we have seen our solver not working in the way that we expect with the settings that were tested before with smaller cases. And we presume the reasons may be of bad interpolation, or as well important information missing from the ILU smoother. So the ILU smoother is also very challenging to parallelize efficiently. Okay, last slide, please. To conclude, the only linear solver that we have been able to achieve a theoretical rate of convergence was the selection AMG. We have tested different variants of how to represent the block matrix as a scalar matrix to do the setup phase of the SAMG. And we have concluded that using the pressure equation is the most natural and efficient way. So choosing the pressure Poisson as the criterion. So the number of course levels is not controlled by the user. It is done naturally in the coarsening phase. And we only control the number of cells on the coarsest level, where we expect the error to be completely eliminated. But this can affect the execution time. So sometimes I have done tests by limiting the number of equations onto a higher number. For example, we use 20 by 20 on the coarsest level, and then I switched to 500 by 500, and this provided better results. So this is also based on different types of cases. Nothing was, we didn't notice anything which appeared regularly to say, okay, this is what you should use. So this is something that should be tested for every case. The choice of smoother is also quite tricky. And this is why we're still working on polynomial smoothers, which we hope will be competitive with the ILUC, which was up until now the most efficient and the best one for converging the Block-coupled system. And we also gave some recommendations on setting up SAMG. And in the end, the thing that I always say is be careful about the mesh that you start with. A good computational mesh can dramatically improve your simulation in terms of both efficiency and results. So starting with a good computational mesh may resolve many problems that we have with convergence. Okay, I tried to be quick, but as I see that the time we went into coffee.
Yep, no problems of